All right, so this is Math 150, Section 2, Lecture 21, give or take. We're now moving into our third and final unit, sequences and series. I know some of you have seen a bunch of this material in high school or other classes. Some of you have not. In some sense, this is going to be the most useful material that we're looking at. It all comes down to trying to approximate very complicated things in the real world by rapidly converging sums. And then how do we analyze them? How do we figure out what their values are converging to? So the first thing is, where do we see things like this? How many of you, the noise is a little distracting. How many of you have seen streaming video? How many of you are awake right now? I think by now everybody should have seen some streaming video at some point in their life. So, yes? Netflix would count, right? So you are getting the content from some other place and it's transmitting it to you. How do you transmit such massive amounts of data? So let's start off by the motivating example that we're going to work towards, our Taylor series. So we've seen the Taylor series for at least one function already. We've seen e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, or the sum n goes from 0 to infinity of x to the n over n factorial. And the idea is the subsequent terms are getting smaller and smaller and smaller for any fixed x because n factorial grows so rapidly that no matter what x you take, this will always converge. And that the more terms you take, the better approximation this will be. You always have to prove stuff like this. So in general, we're going to take some function f of x, and we're going to try to approximate it. So this is one of the main ideas of Calc 1. If I give you a general complicated function, locally, what do you try to replace a function with? Tangent line, straight line, tangent line. If I gave you a function of 2 variables, what would you replace it with? Tangent plane. 3 variables. Hyperplane. And we'll probably just keep saying hyperplane as the dimension gets higher and higher. We're not going to have a hyperplane. Okay? Well, if all I know is the value at the origin, if I had to guess where will I be at time x, I would just say I haven't moved. That's the best guess I can give. If I know my instantaneous speed, I can do a little bit of it. I'll do the tangent line. And I'll do my instantaneous speed times the time elapsed. If I know the acceleration, if I know the second derivative, I'll do an f double time of 0 over 2 factorial x squared. And by putting in 2 factorial, when I take two derivatives, the 2 and the 1 come down, cancel the 2 factorial, and the derivatives match up. And the hope is that this will equal your original function. And we'll write this as the sum, n goes from 0 to infinity of an x to the n, where an is the nth derivative at 0 divided by n factorial. It starts getting annoying to write an arbitrary number of primes, so we put the n in parentheses to represent the nth derivative. And the big question is always going to be, when does the series converge, and when does it converge to the function? If you want, you can view this as we are expanding our function in an infinite dimensional vector space. The first direction is the one direction. The next direction is the x direction, then the x squared direction, then the x cubed direction. So this function would be 1 unit in the one direction, plus 1 unit in the x direction, plus 1/2 of a unit in the x squared direction, plus 1/6 of a unit in the x cubed direction, and so on and so on and so on. So this should give you a little bit of a sense of how difficult this problem is going to be. We're now working with an infinite dimensional space. Okay? Let me show you how this can be used in principle to study things such as streaming video. I'm going to lie and simplify a little bit, but the general idea is true. And this is hopefully going to motivate why we're going to spend so much time on this. If you don't really care about this material, please stop watching anything on your devices. Except, of course, for the class videos, which you are, of course, watching and emailing me when you don't watch. So imagine I have an image that I want to transmit. I have a picture. So you often have a bunch of pixels, different colored dots. And if you have to transmit every single dot, it's going to be very expensive. But you have one thing going for you. Does anybody watch streaming video on either like their phones, Fitbits, old calculators? Good. Oh, you do? Oh, sorry, I shouldn't say phone, sorry. Fitbit, watch, I meant to say watch, sorry. Fitbit, watch, or calculator. No, you use your phone, you use your iPad, you use your computer, you use a TV. You use something that has a decent processor. What this means is you don't have to transmit every bit of information. You just have to transmit enough information to be able to rebuild the image. If you think about how music is transmitted, there's different talks about what level media quality do you need for the human ear. It doesn't have to be perfect. If I can't tell the difference, I can't tell the difference. So I'm going to split my image into 3 different colors. Bless you. Anybody know what the 3 colors are? Yes. Red, green, and blue. And I'll give you the red of each pixel, the green of each pixel, and the blue of each pixel, and then by combining them, I'll know the color. So I'm going to have a function of 2 variables, r, x, y, g of x, y, and b of x, y. And then rather than transmitting every pixel color here, I'm going to have this 2-dimensional red function. Yes?
Is it red, green, blue, or red, yellow, and blue?
It's red, green, blue.
Okay. I thought red, yellow, and blue are like the cardinal colors. Because yellow and blue would make green.
I'm pretty sure they use RGB.
Okay.
And they talk about the RGB values. There's also the flip image of these that sometimes are used for other things. And there are interesting choices as to which colors do you want to do. But the standard ones are the RGB. You can, of course, make some swaps around, and if you have this color, you can get this one instead. So all I need to do is I have this 2-dimensional red function. And what I'll do is I'll do a 2-dimensional Taylor series. And the hope is if I only transmit a few coefficients, I can do a really good job of approximating this function. And now rather than transmitting every pixel value, I just have to transmit a rough approximation. And instead of using 1x squared, it turns out it's better to use sines and cosines. But it's roughly the same idea as a Taylor series. It's just choosing a different basis. And this is how we can transmit information so well and so easily. And then we have the powerful computers that take this and build up that function. And then there's a lot of things you can do. If there's very little movement, you may not want to do much sampling in that area. Lots of things you can do. The real danger is when you have sharp differences, because then the color here could be very different than the color in one other place. So there's a lot of great mathematics and physics to try to figure out, and computer science, to try to figure out optimal ways to do these things. But this is roughly what's going on and why we care about this so much. All right. So this is motivation. So we had the basketball game originally, and so the goal is to figure out what is the probability that the first player wins. And the mathematics behind this is going to lead to the geometric series. We've seen the geometric series before, but this is so important. I want you to see it 2 different ways. Almost everything we have in this semester is going to come down to the geometric series. So how many of you have seen the ratio test at some point in your careers? Root test. Okay, integral test. Okay, so there's a bunch of tests that you can use to determine if a sum converges. The comparison test is compare your sum to something that you know converges or diverges. If you are always smaller term by term that something converges, then you converge. If you're always larger term by term that something that diverges, you diverge. The difficulty with this is you need to figure out what to compare it to. And that's a little bit of an art. It's a lot like factoring a polynomial. If I give you a quadratic, you can sometimes stare at it and just see the factorization. And sadly, the more years you spend doing this, the easier it is for you to see the factorization. What if you don't see the factorization? After you curse and swear for a little bit, what do? Quadratic formula. We have an out. The ratio and the root test are essentially like the quadratic formula. It's very mechanical. The comparison test is art. Trying to figure out what should I compare this to. The more times you do it, the better sense you have of what you should compare it to. But it turns out that the ratio test and the root test are also using a comparison test. They're just hiding under the hood what they're comparing it to. And they're comparing it to a geometric series. This is our go-to. This is the building block. So here's the basketball game. I am choosing Bird and Magic because I'm the professor and I can. I still root for the Celtics, but I go back to the 80s and the old classic, Bird Magic rivalries. How many of you have seen the Super Bowl commercials, Bird versus Jordan? Or seen at least the movie Space Jam? Okay. I should probably update this to Bird versus Jordan, but I still am in the Magic era. So I want to try to figure out what is the probability, they're playing this game of hoops, first basket wins. What's the probability Bird beats Magic? Well, let's let P be the probability Bird gets a basket. Next letter in the alphabet is Q, so maybe we'll use Q as the probability that Magic wins. The problem with this is people often use Q as a shorthand for 1 minus P, for the probability that something doesn't happen. So I'm going to use a little bit better notation. I'll use P sub B for the probability that Bird wins. Well, if P sub B is the probability that Bird wins, then I should probably call this P sub n. And now we want to calculate what is the probability Bird wins. So X is the probability Bird wins going first. And as we saw today, it can be an extreme advantage to go first. Does it seem fair that our second shooter had no chance? Could have volunteered to go first, right? Could have been more assertive, right? This game would strike me as unfair. Not all games in life are fair, right? So let's calculate. What's the probability Bird wins on his first shot? So probably, yes. It's just PB. Alright, so Bird shoots, gets a basket on his first shot. Wonderful. What's the probability Bird wins on his second shot? Yes.
1 minus P, B times 1 minus PM.
Good.
Times PB.
Excellent. So for Bird to win on his second shot, both Bird and Magic must miss on their first shots. And so rather than writing this every single time, let's just denote that by R. So we're going to break the probability that Bird wins into a bunch of exclusive cases. Bird can't win on his first and seventh shot. So to find the probability Bird wins, we just have to sum the probability of winning on each of these shots. What's the probability Bird wins on his third shot? Yes?
R squared PB.
Excellent. So Bird misses, Magic misses, Bird misses, Magic misses, and then Bird gets it. And then the pattern just continues. R cubed, PB, and so on. So we notice every single term has a PB. We factor it out, and we get 1 plus R squared plus R cubed. So we have a geometric series. Yes?
Why is it 1 minus PB times 1 minus P?
So if Bird wins on Bird's second shot, the only way Bird can get a second shot is Bird must miss his first shot. So that's the 1 minus PB. If Magic makes his shot, Bird can't win on his second shot. He never gets a chance to take his second shot. So for Bird to win on his second shot, it must go miss, miss, hit. For Bird to win on his third shot, it must go miss, 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 hit. And so on and so on and so on. So this is a geometric series. If we knew the geometric series formula, we'd be done. I'm going to show you now another way to get the geometric series formula. We did an algebraic proof earlier in the semester. I want to do a more conceptual one. I'm just trying to see if this is going to kill the recording. Looks like, we'll see. So now, memoryless process. Let's calculate the probability that Bird wins. So Bird could win on his first shot. What's the probability Bird wins on the first shot? It's just PB again. The light is causing too much glare. Now, imagine Bird misses and Magic miss. What is the probability from this moment in time that Bird wins? No, PB is the probability that Bird wins on this shot. I just can't. What is the probability that Bird wins eventually, given that he and Magic have both missed? What is the answer? Nope.
PB ought to be there.
Nope.
PB plus R.
Nope.
PB
What is X defined as? The probability bird wins, given that bird shoots first. Given that they both missed, what's the probability from this point onward that bird wins?
X.
It's X. We've just reset the game. This is the key idea. We have reduced ourselves to a previous configuration. It's not often that you can do this. If you can do this, this is wonderful. Most games in life, you do not ever have a repeat. Can somebody give me a game where you can have a repeat?
Any video game.
No, because some video games have a time limit for a level. So it would have to be, so you could have a Pac-Man game where you could have a board cleared to a certain level, and then the ghosts get back to the exact same position as before, and you're in the same position as before, the same number of lives as before. So you could do something like that. So that would work. But it has to be something where there's no time limit.
Minecraft.
I'm sorry?
Minecraft.
Minecraft? I'm just a little bit worried about the time component, so I'm trying to go back to board games. I mean, for Minecraft, is the cities evolving over time?
I don't really play that often, but I assume.
Right, that's why I'm a little bit worried about Minecraft.
I was gonna say like the later rounds of the shootout,
Okay.
because after like let's say both teams, it's like the same situation. If both teams miss, then it just resets.
But if you're doing a shootout, you have different players who have shot. And so you would have to go through everybody. So you could do this. You go through every single person, and then you get back to the one and done, and then that would work, yes.
2048.
2048. To get back to the exact same position.
Yeah. That's when like you have no many moves, you don't have any.
I'm not sure about 2040 because as the pieces are falling, aren't the total sum of things on the board always increasing?
Yeah,
As-
but then when you can't move anymore, you go back to the same spot. You gotta start over again.
But then it's a new game. Then the game's over and you've lost.
Yeah. Could it be like Tetris?
So,
You could do like 50 play before, and it's like reset.
right, but do the pieces speed up? So, chess, checkers, backgammon. All right, things that you can do with actual physical objects and not on a. So chess, you could actually have a repetition of positioning. And in some versions of chess, if there's a threefold repetition in state, the game is declared a tie. Checkers, you can have the same position again. Backgammon, you can have the same position again. Okay? But you've got to be very careful. It's got to be completely the same. In real life, if Larry Bird and Magic Johnson are shooting for 3 straight hours, they're probably getting tired, and their probability of getting a basket is probably not constant. This is the idealized Larry Bird, who won a lot more championship rings.
Magic cannot shoot that.
Well, as a Celtics fan, I'm not going to argue about it. So we have x equals pb plus rx. We want to solve for x. So we get 1 minus r times x equals pb. So we get x is pb times 1 over 1 minus r. But x also equals pb from before times 1 plus r squared plus da da da. And there's our geometric series formula. So we were able to get the formula by interpreting this as a basketball game. Now, it's always good to check and see, is the answer reasonable? And for what values does it work? So remember, R is 1 minus PB times 1 minus PM. What are the possible values of R? What's the smallest R could be? What's the largest R could be? So how small could R be? 0. So how would R be 0? Yes? If neither one? Oh, if either one. If either one, yes. And in fact, from class today, we know that that could potentially arise. We do not yet know that our first shooter is perfect, but we can't rule that out. So it is possible to have a 0, in which case the game is quite boring. What's the largest R could be? 1. What would it mean for R to be 1?
Neither of them were equal.
They suck, right? Now, this is designed to come from the real world. Bird and magic do not suck, right? They should each have some positive probability of making the basket. Well, what would happen if neither one of them could make a basket? What's the probability that bird wins? It should be 0. So what we can do is we can go in and see what would happen. Well, if r equals 1, we get 1 over 1 minus r. That's 1 over 0. What's 1 over 0? It's undefined, but it's essentially infinity. Because if you take the limit as PB and PM go to 0, I'm sorry, as PB and PM go to 0, you're going to be a number that's a little bit less than 1, so this will be a small positive number. So this should be going to positive infinity. Our formula should not be predicting bird has an infinite chance of winning when they both can't make a basket. But we multiply by PB, and what's PB going to? If neither one of them can make a basket, what's PB going to? 0. So we get 0 over 0. Good. It's undefined, and then we're not getting an answer in that case. So you always want to see, is your formula reasonable? How far can you push it? Unlike what we did in class when we multiplied by r, subtracted, telescoped sums, this only works if r is positive. So as a nice extra credit exercise, prove that this also holds if r is negative. So I'll remove the equals 1, because the series will not work there. But show that if you know that this result is true for r that is positive between 0 and 1, it's also true for r that is negative between 0 and 1. But you will no longer have a geometric or probabilistic interpretation because we can't have negative probabilities. So as the semester is ending, I'm trying to put in a few more challenging problems. So for those of you who are thinking of going further in mathematics, you have something to really try your hands on. I'm also trying to decrease the number of standard homework problems so you do have time to play with some of these more challenging problems. All right. Any questions on the basketball game? All right, so I want to do another motivating example. And so we've talked a lot about applications of the calculus we're doing in probability. And so I want to go back to one of the most important functions in probability, the standard normal. So it's going to have density f of x is 1 over square root of 2 pi e to the negative x squared over 2. This is the bell curve, the Gaussian, the standard normal. It looks something like this. And so its cumulative distribution function is the probability we take on a value at most little x. So this is the integral from negative infinity to x of 1 over square root of 2 pi e to the negative t squared over 2 dt. I can't use x as the dummy variable because I'm trying to calculate the probability up to x. I want to evaluate this integral. Unfortunately, we don't have an antiderivative for e to the negative t squared over 2. There's just no nice function that has that as its derivative. So any thoughts as to how we might be able to understand the exponential? How's the exponential defined? What does e to the u equal? It equals e to the u, but how would you actually compute e to the u? What's our definition of e to the u?
Taylor series.
Taylor series. It's the sum, and it goes from 0 to infinity, of u to the n over n factorial. So I can pull out the square root of 2 pi. That's not going to affect the integral. I integrate t goes from negative infinity to x. Then I'll have the sum, n goes from 0 to infinity, of negative t squared over 2 to the n over n factorial dt. And now I have an integral sum. How should I handle the integral sum? What could I do? What are my techniques to handle what's essentially a double integral? Change the order. So Cam, Kale, and I, we watched the old Cam, switch sums video. Anybody remember what Cameron had, how Cameron justified switching the sums? He waved his magic bubble wand. Right? If you do not have a magic bubble wand, and I don't think anybody does, you need to justify it. But let's just switch sums and see what would happen. So if we just switch sums, we have 1 over square root of 2 pi. We have a sum, and it goes from 0 to infinity. I'll pull out the negative 1/2 to the n over n factorial. And in the integral, t goes from minus infinity to x of t squared dt. Oh, that's a really nice integral. Right? What function has derivative t squared? T cubed over 3. I evaluate this at negative infinity and x. What do I get? I get x cubed over 3 minus negative infinity. I'm sorry, I get x cubed over 3 minus negative infinity cubed over 3, which is positive infinity. So when I put this in, I'm going to get an alternating sum of infinities. Now, the answer has to be well defined. It's just the area under the curve. We know the area under the whole curve is 1. It's a finite number. Unfortunately, the series that we wrote down does not converge. We are playing with infinity infinitely often, which is not good. What that means is we need a better way to handle something like this. So for extra credit, I can think of 2 ways to handle this sum. One really good and one good. So see if you can find a way to make sense of this value. This approach is not going to work. And in fact, this is a nice way to review Fubini's theorem. When can we switch orders? If you take the absolute value and it's finite, when you integrate, then you can switch orders. And if you put in the absolute value, then we just get infinitely often with no cancellation. Okay, can't justify the interchange. So we need a new way to evaluate this function. So for extra credit, try to find a way to get a reasonable answer. There is a beautiful, elegant solution to this, which we will see later. Okay. Any questions on this problem? So this is motivation right now for why we care so much about sequences and series. How many people here are econ or potential econ? All right, good. I know some people in the previous class were already talking about multiplier effects. Have you guys hit multiplier effects? So you look at what are people's marginal propensity to consume or save. And let's say people spend 80% of every additional dollar they get. Then you might want to figure out what's the stimulus effect of putting more money in circulation. And if everybody spends 80%, well, you give me $100, I will then spend $80. And then the people who get the $80 will spend maybe 80% of that, and then that will give you another $64 of spend. And it's an infinite geometric series. And sadly, it converges, so you don't have an infinite effect. But then you can figure out exactly how much bang do you get. All right. So I want to talk about a new problem. This is one of my favorite sequences and series in mathematics. There are 2 great quotes of it. The first is by Kakutani, who said he traveled around the country and he would explain the problem to colleagues at the different schools he would visit, and they'd go, oh, that's not too bad. And then a month later, they would give up in frustration. And then there's the great Paul Erdős, who said mathematics is not yet ready for problems like this. So this problem is extremely hard. If you are able to solve this problem, not only will you get an A+ for this course, I will arrange for you a PhD from Princeton University. I still have contacts there. I will also get you a shitload of prize money. Okay? I'm quite confident in making these claims. Why do you think I'm so confident in making these claims? Not only has no one solved it, but a lot of good people have worked really hard for a long time. That doesn't mean that there's not an easy solution that we've all missed. This has occasionally happened. But I'm willing to play the odds. Before class next time, I will tell you about the, I think, $600,000 bet I made with admissions a few years ago. Okay. So 3x plus 1 problem is defined as follows. I was very confident on this bet. So the n plus first term in the sequence is defined as follows. It's 3 times the previous plus 1 if an is odd, and it's an over 2 if an is even. Sometimes they define it slightly differently, and sometimes they might define an plus 1 is 3an plus 1 if an is odd, and then an divided by 2 to the k, if an is even, and 2 to the k divides an, 2 to the k plus 1 does not divide an. And we sometimes write that as 2k double divides an. To just let you know, that's the highest power of 2 that divides. It's just really good notation. It lets me know, for instance, maybe 2 to the 5th divides my number, but 2 to the 6th doesn't. And the reason is, if the number's even, you just keep pulling out powers of 2. So why waste time and have the series longer? Why not just be a little bit more fast and efficient? Okay? There is one small number I want you to stay away from. I will just gamble that nobody will say it. Can somebody give me a reasonably small number?
3.
3. So 3 is odd. So I multiply by 3 and add 1, I get to 10. 10 is even, I can pull out 1 power of 2, so I get 5. 5 is odd, so I multiply by 3 and add 1, I get to 16. And now I pull out all the powers of 2 I can, and what does 16 go to? When I pull out all the powers of 2, 16 goes all the way down to 1. 1 is odd, so multiply by 3, add 1, I get 4. And then what does 4 go to? 1. And now you just loop. Somebody give me another small number. Other than 10, 5, 16, 1, or 4. Because I already know what happens to those numbers. 11. 11 is odd, so it goes to the big poppy, 34. Right? 34 is even. Divide by 2, get 17. 17 is odd. Multiply by 3, add 1, get to 52. 52 is even. Divide by 2, get 26. Divide by 2 again, get 13. 13 is odd. Multiply by 3, add 1, get 2. 40. And what do you get from 40? Where does 40 go? 5. What's your conjecture? No matter what you start with, eventually you hit what? Loop. Which loop? The 1 for loop. Hit the 1 for loop. And then you're stuck there. So this is a conjecture. No matter what starting value you have, you will always get here. So I wrote a paper with a colleague many years ago on this. We looked at the distribution of the first digits if you have a very large starting seed. And approximately what we showed is that there was a bias in these. That about 30% of the time the first digit is a 1, about 4.5% of the time the first digit is a 9. This bias occurs in a lot of data sets all over the world. The IRS uses this to detect tax fraud. And I've actually given some talks at the IRS on using mathematics like this to detect, not do, but to detect tax fraud. Completely open. And it turns out that this problem is related to some of the most interesting, challenging mathematics that's out there. What I love is it's very easy to state. We do not know that every sequence will terminate. All right. Let me do another one. Who remembers the Lycherl numbers from the video? What's the keyword to associate with the Lycherl numbers? This is the palindrome problem. So you take a number like 16. If it's not a palindrome, you flip the digits and add. And you get a palindrome. So as soon as you get a palindrome, you stop. So with a starting value of 16, that would be my sequence. So let's say I take 29. 29 is not a palindrome, so I flip. I get 92, and I get 121. Okay? So let's take another one. Let's take 859. If I flip, I get 958. 9 and 8 is 17, 10, 11, 17, 18. All right, is that a palindrome? So I flip. 7, 1, 8, 1. So I get 8, 9, 9, 8. So for this one, it would be 859, 18, 17, 8, 9, 9, 8. Based on this data, what might you conjecture? What might you conjecture? Yes.
Sorry, no, I don't know.
Okay.
Or if it's 3 digits, if the sum is 3 digits, that there's 3 different units in the series.
Well, but I get it. So you could always I could always give you a really nice generic number like 101. Well, 101 is not a palindrome. 123, 321, 444. So it's a good thing to try, and then I can disprove that one fairly quickly. But what does it seem like will always happen?
All starting numbers eventually result in a palindrome.
Yeah, that no matter what number you start with, you eventually end in a palindrome. We actually have heuristics, I believe, that show almost every number does not end in a palindrome. And we don't have any examples of a number we can prove does not end in a palindrome. I believe 197 is the first number we believe goes off to infinity and never hits a palindrome. But I believe we are in the situation where we don't have even one example. So there's a lot of sequences and series that we can just write down that are interesting, either just because you happen to find problems like this challenging, or they are analogs of problems that are more interesting. So the 3x plus 1 problem, what's the probability a number is odd? If I give you a random number, 50% of the time it's odd. What's the probability it's even and divisible by 2 but not by 4? So what's the probability I have an even number that's a multiple of 2 but not a multiple of 4? It's a quarter. What's the probability my number is even? That's 1/2. And then half of those numbers will be multiples of 2 but not of 4. What's the probability of a multiple of 4 but not of 8? That'll be 1/8. Probability of a multiple of an 8 but not of a 16? That'll be 1/16. So you can view the 3x plus 1 problem almost as a random system. It's not. It's completely deterministic, but you can try to model it as a random process. And then you get some idea of how these random processes behave. And that can be used to model a lot of different things. So what I want to do now is we've got about 10 minutes left, is I want to start introducing some of the terms and some of the things we're going to be studying in the last unit. So a sequence is just a collection of terms. A series is when we sum them. And we often want to know, when does the sum exist? So the first question is generalizing some stuff we did earlier about limits. So we say the limit of a sequence, say an, sometimes we start at 1, sometimes we start at 0, is a if for all epsilon greater than 0, there exists an n such that for all n greater than or equal to n, the difference between an and a is less than epsilon. So the way you should view this is we're playing a game. You choose a tolerance, an epsilon, and I have to choose an n such that as long as I'm at least that far down in the sequence, I will always be within your tolerance. So note that n almost surely depends on epsilon. Maybe the smaller you take epsilon, the larger n you have to be to ensure that you are close. If I want to be within 1 over 100, that's not as hard as being within 1 over 10,000 or 1 over googolplex. And just graphically, if this is a and this is epsilon, maybe this is a1, a2, a3, a4, a5, a6. From some point onward, if the series converges to a, we must always be close to a. So very similar to what we did with limits before. And this gives us a nice lemma. The limit is unique. So not every sequence has a limit, but if the limit exists, it is unique. And so here's the proof. I'm going to do proof by picture. Imagine we had two different numbers that were limits, a and a tilde. They can't be the same number. So let's let epsilon be less than 1/4 the distance between A and A tilde. And the reason I'm choosing less than 1/4 is when I now draw my little windows about them, the windows are separated. If I chose epsilon to be, say, twice the distance, then this would come all the way past here, and this one would go all the way past there, and you could be simultaneously close to both. But by choosing my windows really small, because these numbers are separated, I can't be simultaneously close. What does it mean for A to be my limit? It means eventually all my numbers are very close to A. What does it mean for A tilde to be my limit? It means eventually all my numbers are very close to A tilde. Well, I can't be simultaneously close to both of them because they're well separated. You think of it as, I cannot be in both Massachusetts and California. Can you be in Arizona and New Mexico? Yes. You can be in Arizona. Why can you be in both Arizona and New Mexico?
I think Arizona borders.
Yeah, Arizona and New Mexico borders. You can just go like this. You can actually be in 2 more states as well, right? What other 2 states could you be in? Utah? Not Nevada. I'll leave that as a close. This is the Four Corners Monument, where you can actually be in 4 states all at once. It's the only place in the country you can do that. Okay? So we can't be in 2 places at the same time if they're well separated. All right. So the last thing I want to do today is talk about the differences between necessary and sufficient. So a lot of times in proofs you have, this is a necessary condition, and you have, this is a sufficient condition. Can somebody give me a difference informally between necessary and sufficient? Anybody want to try the difference between necessary and sufficient?
Necessary is you have to have it.
You have to have it.
Sufficient is like it's good enough.
It's good enough. So can somebody give me a necessary condition to pass one of my classes? Take it. Okay. I do know students who have passed classes that they haven't taken. They've withdrawn from the class, and certain professors don't actually check and still just give out certain grades. And I have been at institutions where people have passed classes they have not taken. We have quality control here at Williams. You must take a class to pass it. Is enrolling in the class sufficient to pass? No. I have a conjecture. No one who has consistently come to office hours has ever failed any of my classes in over 20 years. It's not a proof, but I'm very confident about that conjecture. Okay, so let's do necessary versus sufficient. So I give you a sequence, an, n goes from 1 to infinity. We're going to let Sn be the partial sums. It's going to be the sum, n goes from 1 to n of am. It's a1 plus dot 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 plus an. It's the sum of the first n terms. And the question is, when does Sn converge? If we know it converges, what's the next question we would ask? What does it converge to? Sadly, there are a lot of times we can prove that something converges without knowing what it converges to. If you can't figure out what it converges to, can you at least approximate what it converges to? I do some work in a field called linear programming, which has a lot of applications in the real world to helping companies find efficient solutions. A lot of times we don't have enough computational power to find the optimal solution, but we can at least find something that converges to the optimal and can be within a certain tolerance. If you are American Airlines, what is your objective? What's the goal of American Airlines? Make money. Anybody who is majoring in econ and cannot answer this question right now, you've got to rethink what you're learning. Right? Your goal in business is to make money. How does American Airlines make money? Hopefully by flying people, not by taking subsidies not to fly people. You want to find good, efficient routes. So if you are flying people and you have schedules that are bringing revenue on the order of millions to billions of dollars, to be $15 away from the optimal, not a big deal. Especially since you have to estimate so many parameters. So a lot of times just being close is more than enough. So a necessary condition for the sequence Sn to converge is an must go to what? So what must an go to if you want the series, if you want the set of partial sums to converge? What must an go to?
0.
It must go to 0. If it doesn't go to 0, then that means there must be some epsilon, say 1 over 100, such that infinitely often we have a term that exceeds 1 over 100. So then we're trying to figure out what the sum converges to. Boop! Infinitely often we get this push of at least 1 over 100. So we can't be converging because we're getting these large movements. So it is necessary for the terms to go to 0. Is it sufficient? If the terms go to 0, must the sum converge? No. Life would be a lot easier. This part of the course would be a lot shorter if that were true. Not sufficient. We've seen an example of an infinite sum where the terms go to 0 but it does not converge. Anybody remember that? Harmonic series. 1 plus 1 half plus 1 third plus 1 fourth plus 1 fifth plus 1 sixth plus 1 seventh plus 1 eighth plus 1 ninth. And I'm going to stop. Here is a review of the quick proof that it doesn't converge. 1 third plus 1 fourth. Each of these terms is at least 1 fourth. So this sum is at least 2 fourths or 1 half. So that's greater than 1 half. 1 fifth, 1 sixth, 1 seventh, 1 eighth, they're all at least 1 eighth. I have at least 4 eighths, also known as 1 half. So this proves that the harmonic sum diverges. So it's not enough to know that the terms go to 0. All right, this is a good place to stop.